Hi, everybody. This is lecture 31, Wednesday, April 8th. We're discussing chapter 9. We're going on to chapter 9. Remember, Friday is an exam. It covers the sections of chapter 8 that were not covered on the previous exam. So sections 3, 4, 5, 6, 7, 8 of chapter 8. When I decided to go ahead and start chapter 9 because this first section of chapter 9 is not terribly hard, and we do need to keep moving, but I wanted to give you some more time to digest chapter 8 stuff without having too much new hard stuff to do. All right, parametric curves, section 9.1. The idea of parametric curves are that they're curves in the xy plane where x is presented at where you know x is a function of some variable t. And y is a function of some variable t. So t is the variable. And we also use the word parameter. So as in something that you can vary. So there we go. I want to just do a bunch of examples today. Example 1. So given parametric equations, x equals 1 plus square root of t, and y equals 3 minus t. Sketch the curve by using parametric equations to plot points. So sketch the curve by using parametric equations to plot points. So I'm going to abbreviate parametric equations, PE. And I want to notice the form of this problem. It's helpful, I think, for you to pay attention to the kind of big picture of the problems that you're asked to do in the homework. I'll also note that remember that there are problems that are on the homework that are not in WebAssign. You know, they're on this sheet of homework problems that I handed out the first day of class and that are also it's on the web page. There are some problems that are in here that are not in WebAssign. They're the ones that are underlined. And you know, if there are problems like that, it's because I've decided they're very important. They're too important to skip. You know, what's in WebAssign is what's easy for WebAssign to do. It's not like these are the best problems. It's these are the ones that we can easily come up with some way of making a computer version of. So if something's not in WebAssign, it doesn't mean that it doesn't matter. It just means that it's not convenient to make a computer version of it. So you need to be, reading the book, doing examples, and looking at that homework list and doing problems that are underlined. Okay, so the problem is of form given the parametric equations with one linear and one not linear. And then being asked to get points and then plot points. That's the form of this problem. Now, I'm pointing that out because in your homework you have some of this form of problem where both parametric equations are linear equations. Those are easier. There are some where neither of them is linear. There's a whole batch of them where one or both of them was a quadratic function, so as in like a second degree polynomial. But the form, the approach is the same. All right, raise your hand if you notice any restriction that we have on the variable t. Yeah. Can't be negative. So t has to be greater than or equal to 0. We must have t greater than or equal to 0 for the square root of t to exist. So we don't have any other information about this. So let's make a table of values. So let's make t and x, which is 1 plus square root of t, and y, which is 3 minus t. And let's make a bunch of values. So t equals 0, 1, 2, 3, 4, and so forth. This is the usual stuff. Okay, when t is 0, x equals 1 plus square root of 0, so that's 1. Y equals 3 minus 0, so y is going to be 3. When t is 1, x is 1 plus square root of 1. That's going to be the number 2. Y is going to be 3 minus 1. That's going to be 2. Okay, when time is 2, what's x?
I just put 1 plus square root of 2.
Yeah, which is a pain, right? I mean, they didn't tell us what values of t we had to use. It was my bright idea to make this usual table. But it turns out that these values of t are going to be kind of a pain in the butt. What would be the next convenient value of t? 4. So let's just redo our table. We get to, our job is just to make a graph, so let's make it easy on ourselves. So when time is 4, then x is 1 plus square root of 4, that's going to be 3. And y is going to be 3 minus 4, that's going to be minus 1. When x is, what's the next convenient value of t? 9. So in this case, x is going to be 1 plus 3, that's going to be 4. And y is going to be 3 minus 9, that's going to be minus 6. And the next convenient value of x would be 16. So we'd have x equals 1 plus square root of 16. So that means x would be 5. And y would be 3 minus 16, which is minus 13. And let's make one. Well, actually, that's enough. So the graphs, again, WebAssign asks you questions that are easy for WebAssign to ask. So for instance, your job in this problem is to make a graph. On a quiz or exam, your job would be to make a graph. WebAssign, your job is, pick which of these graphs is the right one. And you get unlimited submissions, so you can just click the damn graphs until you click the right one. So it's a very different kind of question in WebAssign. The job of making a graph is a serious thing. WebAssign turns it into kind of a farce. They just present you with some graphs and say, which of these is the right one? So, you should, in making doing your homework, You should be taking these problems seriously, making a graph on paper, and then look at WebAssign and see which of those graphs match. So we need to have the point 1, 3. And this is at time t equals 0. The point 2, 2. That's at t equals 1. And 3, -1. That's at t equals 4. And 4, -6. So notice if this were a particle starting from rest, it's speeding up as it goes. And then 5, -13. This would be t equals 6. And there we go. There's our graph. And notice the arrow gives the direction of the travel as time goes on, but it's good to put another arrow. So again, when you make a graph, you need to label important points, and especially the initial point, if there is one, and then show which direction the graph goes as time goes on. Okay, question B is start over. Sketch the curve by eliminating the parameter. Yeah. Yeah. Yeah.
So can you just write the equation for x in terms of t and plug it into the equation for y? Create a line for graph?
In part B, exactly. Wonderful. Excellent. B, start over. Sketch the curve by eliminating the parameter. Did you have your hand up before I started talking a while ago? Would have been good if you had brought this up instead of me. Well, here we go. By eliminating the parameter to get what's called a Cartesian description of the curve. So we would like to have y as a function of x. So we want x to be the variable. So how should we do this? Well, for now, let's solve the second equation. This is different from the way that I did it before. Let's solve y equals 3 minus t for t. So t is going to be 3 minus y. I add t to both sides, and I subtract y from both sides. And then I'm going to substitute that into the second equation. There's the second equation. So x is 1 plus square root of t, so 1 plus square root of 3 minus y. Okay, we want to solve this for y, right? So let's x minus 1 would be square root of 3 minus y. So that means that let's square both sides. X minus 1 squared equals 3 minus y. And then let's add y to both sides and subtract that square term from both sides. So I get y equals 3 minus x minus 1 squared. So how could we graph this by transformations? I mean, like, give me the sequence of basic graphs and then their transformations that would get you to here. Anybody want to tackle that? What's the basic graph? Annika?
Parabola,
What's the equation?
x squared.
Y equals x squared. So their basic graph is y equals x squared. So that's this baby. What do we want to do next?
Flip it upside down.
Flip upside down. What's the formula for that? Y equals minus x squared. So then we get this. Somebody else, what's next? I'm going to get some more hands in the air. This is some more hands in the air. This is high school transformation of graphs. Yeah. Trent? Raise it up 3. So y equals, what's the formula?
X squared plus 3.
Yeah, so 3 minus x squared. That's not quite what we have, though. What do we need to do now? Some more hands. Somebody from the first 2 rows. We want to get to this. What's the transformation that'll get us from here to here? I'd like some more hands. There's people who haven't answered. Alexander, your hand is kind of up.
Would we maybe move it one to the right, the x minus 1?
Yeah, move one to the right. So we get y equals 3 minus x minus 1 squared. So here's my graph. Is it the same graph? Yeah.
X needs to be restricted to being greater than or equal to 1.
So Kinsey said x needs to be restricted. Where does that come from? Jace?
The original where x equals 1 plus square root.
Yeah, notice x is going to be greater than or equal to 1. Now that's lost here. So this equation gives us that x is greater than or equal to 1. So I need to add that requirement here. So this equation has to be true. This equation has to be true with the extra requirement that x is greater than or equal to 1. So when I get all the way over to here, and x is greater than or equal to 1, that tells me that I have to cut this graph off and only use the right half of it. A lot of students are not aware of how careful you have to be. So for instance, are these equations the same? Do those two equations mean the same thing? Here's another question. Question B. The goal is to find square root of 9. So Frick says square root of 9 is plus or minus 3. Frack says square root of 9 equals 3. Who's right? Frick or Frack? Or are they both right? Trent? Frack, why? Why? Right. So this symbol means that x equals y squared and, it means that y equals x squared and y is greater than or equal to 0. So the square root symbol means the non-negative thing that satisfies that equation. So these two things don't mean the same thing. So the square root of 9 doesn't, to say that y equals the square root of 9 doesn't just mean that y squared equals 9. It means that y squared equals 9 and y is not negative. So you have to pay attention to the square root symbol. And then also pay attention to the, most of the population of the country does not know this. So, half the population is going to say Frick is right. So you have to be very careful when you use the square root symbol. Who are you talking to? Are they going to get it that you're talking about the non-negative number? Okay. So here's here's the Cartesian description. We have to have x greater than or equal to 0. The Cartesian description. So you got to pay attention to the domain. And also, you lose sight of the time evolution here. Here I have the shape of the curve, but I don't know what the time evolution is here. There's no mention of time. Okay, example 2. Given parametric equations, x equals t squared plus t, and y equals t squared minus t, sketch by using the equations to plot points. So remember, the parametric equations I abbreviate PE. So sketch by using the parametric equations to generate points. So remember, I said a while ago, it's useful to keep in mind the big picture of what kinds of questions are being asked. So observe the form of this problem. So we have both parametric equations are quadratic. And then what we're being asked to do is generate points and then plot the graph. So it's the exact same form as the previous problem. It's just that the parametric equations are not quite so simple, a little bit harder. So as I said, you have homework problems of these various types. And also, if you look through the book examples, the book examples start with, I think they start with, well, anyway, you've got, scrutinize those book examples. The one, if there's a book example that has both parametric equations quadratic, and you're asked to do this, well, that would be a good model for how to approach this. Oh, and also, minus 2 is less than or equal to t, which is less than or equal to 2. Well, let's make a table of values. So we're going to start with t equals -2, and we're going to end with t equals +2. But we're going to want to, and we're going to have, in the middle, we're going to have t equals 0. And we're going to have t equals -1 and t equals +1. But it's going to help to have some more points in between. So -3/2, -1/2, +1/2, +3/2. Because you'll see, as we do this, we would not have enough data points to get a good graph if we didn't do this. Okay, so when t is -2, I get x equals 4 minus 2, so x equals 2. And then y is going to be 4 minus a -2, so 4 plus 2, so that's 6. Let's go back down, all the way down to the bottom. When t is 2, x is going to be 4 plus 2, so that's going to be 6. And y is going to be 4 minus 2. That's going to be 4. Okay, let's do the easy points first. The easiest one is when t is 0. Then both of these are 0. And then when time is 1, x is 1 plus 1, so it's 2. Y is 1 minus 1. That's going to be 0. Then let's do the next easiest one. When x is -1, when time is -1, x would be -1 squared. That's 1 plus a -1, so -1 would be 0. And then y would be 1 minus a -1, so that's the number 2. So we're accumulating some data points. 2, 6, 0, 2, 0, 0, 2, 0, and 6, 2. Now let's tackle the harder ones. When x is when x is 1/2, I get when time is 1/2, I get x is 1/4 plus 1/2, so 3/4. Y is going to be 1/4 minus a half, so minus 1/4. Let's look at when time is -1/2. Then x is going to be 1/4 minus a half, so that's going to be minus 1/4. And y is going to be 1/4 minus a -1/2, so that's going to be 3/4. So I've accumulated 2 more points. Minus 1/4 3/4 and 3/4 minus 1/4. Okay, let's look at when x is 3/2. Then x squared is 9/4. 9/4 plus 3/2, that's 9/4 plus 6/4, so that's 15/4. On the other hand, y is going to be 9/4 minus 3/2, so 9/4 minus 6/4, so that's going to be 3/4. And then when x is minus 3/2, I'm going to have 3/4 here, and I'm going to have 15/4 here. So I've accumulated these points, 3/4, comma 15/4, and 15/4, comma 3/4. So when I make the graph, you're going to see why I wanted those in-between points. I'm going to start by graphing the nice points. So 2, 6 is going to be up here. 6, 2 is going to be over here. So this is going to be at t equals 0. And this is going to be at t equals 6. Okay, and then let's go to the next nice point, 0, 2. And the next point is going to be 0, 0. And the next nice point is going to be 2, 0. See, that's not really enough information to graph a convincing curve. It doesn't seem likely that the graph follows the axes is like straight line segments. There's going to be something going on between these points. So that's these other points. So 3/4, 15/4. Well, 15/4 is almost 4. So 3/4, 15/4 is here. And then minus 1/4, 3/4 is about here. And then 3/4 minus 1/4 is about here. And then 15/4, 3/4 is about here. So remember what I said a while ago, my idea in going ahead and starting this section, even though we have an exam on Friday that won't include this stuff, this is kind of an easier day. We're just plotting points. So my graph looks something like this. So this is t equals 0, and the direction of travel is that. Question, say again? T equals minus 2 to t equals 2. T equals minus 2 to t equals 2. Question B is to confirm with Desmos. So I've said before in this class, embrace your inner nerd and take some pride in making these graphs. Again, WebAssign is a joke. You don't have to make graphs for WebAssign. You just get to click until you find one that works. But you want to practice making these graphs. The skill of graphing is oddly satisfying if you're a nerd. And then confirm with Desmos. That's also a skill that you should cultivate because Desmos is a cool tool. So let's plot our graph. We should have t squared plus t. Is that x? Now look, it's asking if I want to make a slider. Okay, let's make a slider. I'm hungry. So let's see. Let's go from t equals minus 2 to 2. And by steps, let's go 1/10. And then we need to have a y-coordinate. The y-coordinate is t squared minus t. Okay, so let's look at the beginning. At the beginning, look, there we are at 2, 6. Can everybody see the coordinate up there? Now let's make time travel from minus 2 to 2, and there we go. Isn't that cool? Now let's get rid of the slider, and then it's going to ask us to give the domain. So minus 2 to 2, there we go. There's the whole graph. It's really cool. Really fun to explore Desmos. Anyway, there's no Desmos classes. You just get better at Desmos by doing examples. And you can look up stuff and find out, how do you get shaded regions in Desmos? How do you can get all sorts of stuff from the web. Example 3. Given these parametric equations, so x equals 3 cos t, 3 sine t, y equals 3 cos t, t between 0 and 2 pi, sketch the curve. Notice they don't say sketch the curve by plotting points. That's a crucial bit of sort of subtle information that's not given. You're not told to plot the points. You can make a table of values, but it turns out there's a sophisticated way. It's simpler, but it's sophisticated because it's something that might not occur to you to do this. So again, observe the form. Observe the form of the problem. So we have parametric equations involving, well, I'm just going to say trig. And then we're just supposed to sketch the graph. Trick. There's a trick here. Anybody notice anything about the x and the y? Excuse me. What do we get? Well, this is what's that? Jace? So in the sciences, you should pay attention to this. It'll often turn out that you have some description of some system where you've got some quantity that looks like this, some other quantity that looks like this. You You always have this trick available that will simplify things. So what do the solutions of that equation look like? What do the points that satisfy that equation look like? Come on, what are the XY pairs that satisfy this? We got stuff to do, people, so please don't be shy. Don't wait for the same people who always raise their hands. Who knows what the graph of this equation looks like? Circle. Centered where with radius what?
Centered at 0, 0. And a radius of 3.
Good. So there's our graph. And so it goes through 3, 0, 0, 3, minus 3, 0, and 0, minus 3. But it doesn't give any indication of the evolution in time. Time goes from 0 to 2 pi. So that just means that we start here and go around, right? Well, no. What's the value of x when time is 0? And what's the value of y when time is 0? In other words, what's the point 0, xy? Annika, you can give me one coordinate.
X is 0.
Okay, somebody else, give me a one coordinate.
Y is 3.
Y is 3, okay. What's the next convenient time to look at?
Pi over 2.
Good. So Liam, tell me one of the coordinates when time is pi over 2.
X be 3 over 2.
X is 3 sine of t. So what's 3 sine of pi over 2? What's sine of pi over 2? Come on, people, let's get some more people involved. Sam? Sine of pi over 2 is 1, so this is going to be, so x is going to be 3, yeah. What's y going to be? Y is going to be 3 cos pi over 2. Sam, you're on a roll.
0.
Good. So there we go. Where are we going to be when time is 2 pi? Well, we know that the x formula is periodic with period 2 pi. So we're going to be back here. And we're not going to be back, well, and the y period is also 2 pi. So we're going to be back there again. So this gives us actually, this is at time 0. And we're going clockwise around the circle. And we're going once. And this is also time equals 2 pi. So getting the equation is easy, the equation for the graph, if you know this trick. Okay, example 4. Find a parametric equation for path that goes 3 times around circle. Counterclockwise. The circle is x minus 3 squared plus y squared equals 25, starting at 3, 5. Well, let's draw this. That's a circle centered at 3 with radius 5. So centered at 3, 0 with radius 5. So here we go, 3, 0, and I want radius 5. So that's going to look like this. It's going to go through 8, 0. It's going to go through 3, 5. It's going to go through minus 2, 0. And it's going to go through 3, minus 5. And we need to go 3 times counterclockwise. So 1, 2, 3. What's the easiest way to accomplish the 3 times around business? Annika?
Set the interval for to t equals 0 to t equals 6 pi.
Good. Yeah. That'll give us 3 times around. We could just go like from 0 to 2 pi and somehow figure out how to make the thing go 3 times as fast. But I think it's easier to just make the interval work. Okay, now we want the values of x and y to fluctuate by amounts 5, plus and minus 5. So we want to have sines and cosines multiplied by 5, so the fluctuations go up and down by an amount 5. But for x, we want the fluctuations to be fluctuating by 5, up and down by 5, around x equals 3. So 3 plus 5, 3 minus 5. We want that to be the fluctuations. So let's use x equals 3 plus something or other. And let's use y equals, well, we want a sine or a cosine multiplied by 5. What sine or cosine multiplied by 5 would give us this starting point? Well, if y were equal to 5 cos t, well, when time was 0, y would be 5 cos 0. That'd be 5. Great. And as time started growing, cosine would start shrinking. So the y values would come down. And so this would be at time equals pi. Y would have gone down to minus 5. Okay, so that'll give us the y values that I want. Y's are going up and down. Now what about x? We want x to start at 3, but then shrink. And at pi over 4, we want x to be 0. That's right, we want x to be minus 2. So what we want here is y equals 3 minus sine of t. So that as time grows from 0, sine starts to grow, so x starts to shrink. So we start here, and as time grows, the sine starts to grow, so x starts to shrink, and it actually begins to go negative. So that's there we go. There's our formulas. So both of these are periodic with period 2 pi, and that does it. I'm kind of in a hurry because I don't want to run late because I want to hand back quizzes. The final example, example 6. Oh, I'm running out of examples. Example 5. We have, I'm just going to cut to the chase here. X is cos t, and y equals secant t, and t is from 0 to pi over 2. Well, notice, so graph this. So notice that y is secant t, which is 1 over cosine t. So that's 1 over x. So the graph of this is going to look like the graph of y equals 1 over x. And when time is 0, cosine is 0 and secant is, cosine is 1 and secant is 1. So at time 0, this graph starts at 0, 0. Now what happens as time grows? As time grows towards pi over 2, cosine actually gets smaller and smaller, closer to 0. But secant gets bigger and bigger. So this graph looks like this. Final example. Given these graphs, minus 1, 0, and 1, 0. I got to take a picture of everybody because I might, if any of you need to leave while I'm still talking, I don't want you to be, I'm going to take attendance by counting the leftover quizzes that I hand back. So if any of you have left, I want to make sure I've got your picture. Okay, so in this problem, we're given two graphs. X of t and y of t. Minus 1, 0 is an intercept, 0, 0 is an intercept, and 1, 0 is an intercept on the graph of y as a function of t. Plot, sketch the curve. Sketch x of t, comma, y of t. So use these to generate a curve. Well, I'm going to do this. I'm going to just make a table. So I've got some easy values when time is -1, 0, and 1. So leave some space here. Time equals -1, time equals 0, time equals 1. At those points, let's see, at -1, x is 0, and y is 0. At time 0, x is 1, and y is 0. At time 1, x is 0, and y is also 0. So we've already got 3 data points on our graph, 0, 0, 1, 0, and 0, 0. Now let's look at some in-between points. Say time is 1/2. Well, when time is 1/2, then x is small and positive, and y is small and negative. Let's look when x is -1/2. When x is -1/2, when time is -1/2, x is small and positive, y is also small and positive. The last thing to look at is when time is large and positive, x is large and negative, and y is large and positive. So t as t goes to infinity, x goes to negative infinity, and y goes to infinity. And let's look at the other end of the graph. Over on the left end of the graph, when time is large and negative, x is large and negative, and y is large and negative. When t goes to negative infinity, both x and y go to negative infinity. So let's plot those three easy points. 0, 0, 1, 0, that's it. That's it for the easy points. But we do know we have a point where x and y are both small and positive. And we have a point where x is small and positive and y is small and negative. Okay. And we're transiting around this little loop this way. We're going around this loop like this. But when time is going to negative infinity, both x and y are getting large and negative. So we're coming in from this way. And when time goes to infinity, x is going to negative infinity and y is going to positive infinity. So we end up with this graph that looks like this. It's pretty wacky. It looks like a ghost flying to the right, or a goldfish with an endless tail. Okay, so there we go. That was very quickly done, I'm sorry, but I wanted to get that kind of example done. All right, let me hand back your quizzes. Thank you, Gabriel. Kinsey,